In today's episode, we're going to see how we can leverage a small amount of type-level programming to develop a more strongly typed interface to a server, a web server or a database server, whatever else. We will see that we can, by doing so, we will not only get a better programmer experience, but also a better on-the-wire protocol. So, sorry, I pressed the wrong button. Here we go.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
51 episodes of Unfolder, and I still get confused by the StreamYard interface. But okay, sorry for that. All right, so let's actually focus on development server here. So let's start with this untyped interface. So we have a server, and the server supports it's a very simple one. Just has two kinds of requests that it supports. It can tell you what the current time is, and it can read a file that you ask for. And then, depending on what you ask for, it has one of two responses: either the current time or the contents of the file. Now, if we have an interface like this, then if we have something like send request, what it's going to do is we're going to take the request as input, and then we're going to get the response as a result, right? Now, of course, the problem here is obvious, right? Depending on the request, we get a different type of result. Like if we ask for the time, we should get back a time. If we ask for a file, we should get back the contents of the file, a string. But this does not tell us that. These types, these Haskell types, don't at all tell us what the link is between what kind of request we have and the type of the response. And so this means that every caller of the server, everybody who calls send request, needs to deal with the case where the response is of a different type than they expect. Even if the server would never respond with such a response, the types don't tell us that, right? So we still have either partial functions all over the place, or we need to deal with cases that don't exist all over the place. So neither of those is good. And also, if we would think about how do we encode response on the wire, like what is the low-level protocol for this? Now, suppose that we are using JSON to communicate back and forth, just as an example. Then the JSON representation for a response might look something like this. We have an object where a field tag tells us if this is a time or a file, and then the payload, which is the actual response itself. But this encoding is also not great, because even if the server always responds to a getTime request with a time, then the result on the wire protocol still tells us, oh, the result is a time, which means that the caller, even irrespective of types, even if you work in an untyped language, you need to decode this, look at that tag, and then deal with the case where the tag is not what you expect. And so this is suboptimal both from the programmer's perspective, like we would like to have stronger types here, as well as from the communication perspective. Does that make sense so far?
It does to me.
Okay, well that's
don't yet have any complaints in the chat. But
okay, well, let's take it as a that everything is good so far. All right. So what we want to do is somehow take these two types and establish a link, some relation between a request and the type of the response. So let's start with these two types here, as we had them before. But now I'm going to turn request into a GADT. So I'm going to introduce another type variable here. And this type variable is going to be instantiated to the type of the result. Right? So getTime is a request. And which value do we use for this type variable? Well, the response to a getTime request is a UTC time. And so this line here establishes a relationship between the request getTime and the type of the response, in this case, UTC time. And similarly for getFile, now this still has an argument, just like before. But then the result is a request, not just for what? Well, a request for a string. Right, so this GADT introduces a relationship between each request and the type of that response to that request. Now, working with the GADT is not particularly difficult, right? For example, I could implement my server as follows. I take a request as input, and I give you back my response. Now, what's my response? Well, it's something of type A, right? That was the whole point. So we can do that. If it's get time, I just ask for the current time. And if it's get file for some file path, I just read that file. All right. Okay. Now let's think a little bit about what happens.
Yeah, we have one question now.
Oh, okay. All right.
So I'm not completely sure I understand the question, but perhaps you do. Why not adding a new root?
Oh, I guess they're asking if you have a different endpoint for get time and a different endpoint for files, then rather than sending a request for that particular thing, you just go to a different route, a different URL, and then you only get responses back for that.
You're just moving the problem elsewhere, though.
Yeah, I mean, then you need to have some sort of a relationship between routes and their responses, right? I mean, and something like Servant does exactly that, right? Servant establishes precisely that sort of thing. But then, I mean, Servant has a ton of type level stuff precisely to make all that stuff clear at the type level. Yeah. Okay. Thanks for the question. I hope that answers it. So let's think a little bit about what happens if we send multiple requests to the server. So let's start with a simple case where we just send 2. And let's just think about the server implementation first. So if we have 2 requests, then we're going to get back 2 responses. And this is actually very simple. We just call exec request on the first one and on the second one, and we just pair the results back up. What did I? Oh, sorry.
Request is not a class.
Yeah, sorry.
Yeah.
Okay, this is quite simple. But what if we want all results? So what if I have a list of results, of requests, right? And then I want a list of responses somehow. So this does, I mean, so this is going to look like, I mean, a request for an A, and then a whole bunch of other stuff, and then a request for Z, right? And then I want something like this back as a result type, right? So we need to generalize from a tuple of length 2 to a tuple of length n. And this structure here, where we have a list of all different types, but with some common structure, right? The common structure is request here. We have a request for the first thing, request for the second thing, the request for the third thing. This structure is captured by what the sop-core library calls an NP. Right? NP stands for N-ary product. And just to give an intuition, something like NP of request of, say, int bool car, you should think of this as being basically the same thing as a list or a tuple, where we have a request of an int, a request of a bool, and a request of a car, right? But since we have a list here, this can be of arbitrary length. So I'll show you the definition of NP from the library. So an NP is either empty, which is like the empty list, right? Or we're adding another element to an existing NP. So we have an NP for X's. F here is this common structure, which in our example is request. And then we're adding one element to the front of it. So then the result is still over this common structure, but then the list is one, the type level list, right, has one element more. And then just like for lists, we have operations like map and sequence, right? Map just applies a function from A to B, list of A's to list of B's, and sequence takes a list of actions, right? You could think of this as request maybe here, to an action of the list. We have similar functions also for N-ary products, right? So for N-ary products, that function looks like this. It looks a little bit more complicated because every element has a different
Probably
type.
actually not so much a list of requests, right? More a list of IO actions.
Yeah, something like that.
Request right now isn't actually in.
Yeah, sure. Yes. Yeah. That was maybe a bad example. Yeah. But yes. Yeah. You're right. Okay. So here, since every element in this list has a different type, we can't have a function from that type to the other type. What this function needs to do is go from the common structure, which in our case is request, to a different common structure here, and then it should work for any argument here. And then there's also an equivalent of sequence, which has the same thing, right? So sequence, here we have a list of actions into an action of a list. Here we have the same sort of structure where if this is an NP of actions, for example, this is an action of the result of the N-ary product. I hope that makes sense. So this.
No, but you just edited this weirdly. Sorry, now it does not make sense to me anymore. Now it says 2F.
Sorry. Did I just delete something? Yes, I did. Sorry.
Yeah.
Sorry, I must have.
And did you say what the I is?
I did not say what the I is. That's a good point. So I here is the
identity. Need it sooner or later.
Yeah, definitely. Yeah. So this is the identity functor. So it's just new type I of A is I of A. Remember, this is used all over the place.
So I mean, products, as Etzko said, are sort of potentially heterogeneous lists, but which typically have some sort of common structure, right? Sort of like you can see it as a list of requests or a list of maybes or a list of IO actions, but the individual things can all have different types. And one special case, which is very common, is that you have a list of identities, then it's just a fully heterogeneous thing, right?
Yeah, exactly. So NPI of, say, int car bool is basically the same thing as I of int, I of car, I of bool, and that's basically the same thing as I int car bool. Yeah. Okay, so this list, this N-ary product of request becomes an NP of request for some types A's. We don't know what that is, doesn't matter. And then the result, after we execute this, we're going to get back an NP where we get all the responses back, which is, and the response, the type of the responses is these A's, right? That's exactly the point of this GDT here. The index of request tells us what the response is. So we get back the I, just the identity here, for those responses. Now, if you think about it, we just want to map exec request over the NP and then sequence everything. That's what you would do with normal lists, and that's exactly what we do here as well. So if you're familiar with like these basic patterns in Haskell, then this should come as no surprise. The only slight complication here is that these functions need what's known as a singleton on this type level list. We actually discussed this a little bit in our previous episode 2 weeks ago. But if you haven't watched that, it's not essential that you understand exactly what this is. My intuition, and people think about this differently, but the way I think of this is sort of saying that A's must be a valid list. Like this must be the structure of this list must be valid. Meaning constructed of nil and cons operations. But even if that doesn't make any sense to you, you can just take this as for granted that this is just something that these functions need, and you just need to propagate it. You don't necessarily need to understand it in order to know the library. Okay, let's see another example where we have a server which doesn't necessarily give you all results, but it gives you back the first result that comes back that we can compute. So, and let's again start with just 2. So if we have a request for A and a request for B, then I want to get either an A or a B, whichever result came back first.
Okay.
And this is also very simple. If we have 2 IO actions, one of A and one of B, then the async library offers us a function called raise. And raise of an IO action of type A and an IO action of type B gives you precisely an IO action of type either A, B, right? It runs both actions, waits for the first one to complete, and gives you back that result. So we can just raise the execution of these 2 requests. Okay, simple enough. Now,
raise is already returning the either. Yeah.
Raise already returns the either. Yes, that's right.
Yeah.
So now we want to generalize this to a bunch of requests. Now, what's going to be the result here? Now the server is going to choose, right? So here it was either. Now, if this is a tuple of length 2, you could think of this as a choice between 2 options, right? So here we want a choice between n options. If we have n requests, we need a choice between n options here. And we're also going to add one more option, n plus 1 options. We're also going to add a timeout. So the timeout is going to be captured by maybe. But now here we need this N-ary sum, right? This choice between n options here. And that exists in the sop-core library, just like N-ary products do, and it's called an NS for N-ary sum. So you can think of this as a generalization of either to N choices.
Yeah, and again, there is this argument. I mean, like NS and NP have the same kind, right? I mean, they both take this constructor argument, which just like an NP is generally a product or a list-like thing of things that may have a common structure, and NS is also a choice between things that may have a common structure. But in this case, we don't need a common structure, so we use the identity again.
Yeah. Yeah, so actually it might be useful to actually look at the definition of an N-ary sum. And here it is. So we have two constructors. Z, you can sort of think of it as injecting something in a sum right here. So if we have a sum with at least one option called X, the first option, then Z says, I have that first option. And S says, well, if I don't want the option here, but somewhere else in the sum, then I can do that by injecting it into the rest. Right? So we're adding something basically into the front of the sum. Another way to think of this is counting, right? This Z stands for 0, S stands for successor. So you could think of something like S of Z of X as being injecting sort of the third option, right? It's the third option in the sum.
Right, into a sum which has at least 3 elements. Yeah.
Yes, that's right. Yeah. Could have more.
So it's like indices into a list or selecting one of many choices and numbering them. Yeah.
So actually, to implement this, it's more useful to implement a generalization of race. So we're going to take race, and it's going to take an NP of IO actions, and we're going to raise all of them, and we're going to get back the result. Sorry, an NP. And before I implement this, let's just first see how we use this, just to motivate it. So what we're going to do is we're going to map, just like before, map execute request over every request. That gives us an N-ary product of IO actions, and then we can just erase them. And so this function is now very simple.
Did you mean raise N to return an NS, right?
Oh, it's NS, yes.
Yeah.
And now the only thing is left is that we need to this single thing. Okay. So how do we define this? Well, I mean, there's many ways that you could define it. I'm just going to use explicit recursion just to show that is possible. And sometimes the more high level, there's all kinds of functions, higher order functions in the sop-core library that you can use to capture all kinds of patterns. But in some cases, explicit recursion is easier. And so for now, at least, I'm just going to use explicit recursion. So if we have the empty product, then actually let's leave this for the second case. Let's actually deal with the non-empty case first. So we have some action that we want to execute, that we want to raise, and a bunch of other actions that we also want to do. So we're going to raise, right? We're going to raise this action with, well, the recursive call to raise n of all the other actions. And so this is going to give us the first result out of the remaining actions, and we're going to raise that with the first action. Now that is going to give us a result, which looks like you can see it at the bottom here. It's either x, that will be the result of this first action here, or maybe an N-ary sum for the remaining actions, right? That maybe would be if we had a timeout. And the sum would be the sum from the remaining actions. So we just need to map this into the result type that we want here. So we have two possibilities, like in either case, right? So we can use either here. So the first one is where we got the result from the first action. So we have a result. So we did not timeout. So we used just for that. And then we have an x that we need to insert into the sum. It's the first element in the sum, like the first index. So that's z. And then we need to deal with this identity functor, so we need to wrap it in I. And then for this case, we have something in a result in the smaller sum, right? But we need something a result in the larger sum, all the index. So if this says, well, this is a result in index 3, then actually in the larger context, this is index 4, right? So we need to increment the index. So we need to fmap to deal with the maybe successor here. And now for the nil case, we're just going to return nothing, dealing timeout after a thread delay. And for here, I'm just going to hard code the thread delay at 1 second, but of course you could make this an argument. That doesn't really matter. Okay. So far, so good. That's dealing with multiple requests and some insight into sop-core, into the key two structures that sop-core offers, N-ary products and N-ary sums. Let's now get back to the serialization, right? When we started this episode, we had two problems, right? One was sort of the programmer's interface, and the other was how do we deal with serialization? So now let's look at serialization again in this context. Now, the first thing to notice is that when we generate JSON from a request, like when we encode a request, the fact that this is a GDT does not get in the way at all. Like we don't need to worry about that at all. So I'm just going to copy in the definition here because this is actually very straightforward. If we have a request, if that is getTime, we just create an object where the tag says getTime. If we have the request is getFile, then the tag says getFile, and we need to record which path we want. And oh, sorry, this is actually this does need a bit of explanation. So let's actually start look at this in a bit more detail. Okay. So we have an NP of requests. What we want to do is turn every request into a value, a JSON value, and then turn that whole thing into a JSON value, which is a list, right? So I have a constructor here with a function called value list, which what it wants is a bunch of values, right? So we have an NP of request, and we want a list of values here. Now, what we're going to see here is a very common pattern. So we have this common structure, right? This axis here, and remember that something like f int car bool was basically the same thing as f int f car f bool. Now, if we pick for f the constant factor, which to remind you looks like this, so kba has two parameters, it's going to ignore the second parameter, and it just uses the first parameter. So kab is just a b, no matter what a is. Right, so that means if we use ka here for int car bool, that will be equivalent to ka int k a car, ka bool. But all of these are just equal to a. So this is just a to a to a. All right, so this is roughly equal to a normal list. So that means that that's a very common pattern in sort of this kind of programming, where we often have different structure, but at some point we collapse all the structures to the same structure, and then we can forget the fact that this is an N-ary product, and we can regard it simply as a list. So sop-core offers a function for this, and it's called collapse. We collapse this structure. So it takes an NP of ka of x's, and now we can ignore this x's, and it's just a list of a's here. Right? That's precisely what I was explaining here. So we want a list out of this, so we're going to collapse this, which means that we now need to turn NP of requests into an NP of k of values, constant values. Well, how do we turn a request of a into a value? We just call toJSON on it, and then we just need to wrap it in the constant constructor. Right? So we just map over the NP k after toJSON, and we're done. Okay.
Cool.
Now, on the server side, things are a bit more difficult. Right? On the client side, we know what kind of request we're sending. But on the server side, we don't know what kind of request we're receiving. Right? And so actually, this is something we talked briefly about at the very end of the episode last week, where we have some type level structure, but we are now dealing with a case where we need to recover this type level structure. Right? We don't know a priori what kind of type we're expecting. And in the last episode, we used continuations for this. In this episode, I'm going to do something slightly different. And use existentials. So what does that mean? Let's see. We want to be able to say that we have a request on the server, right, for some type that we do not know. Now that is precisely what an existential is. It's a type you do not know. So some requests is going
Well,
to...
I mean, okay. I mean, I guess you're right. I just wanted to phrase it, sort of rephrase it in a slightly different way. I mean, it hides some amount of information about your type, right? I mean, some requests, you still know it's a request, but you no longer know what kind of request it is.
That's right.
If you go all the way and forget everything, then, I mean, sure, that's still an existential, but then it becomes useless. I mean, but
exactly. So some requests where we're using the type of the result here, but not here.
Mm-hmm.
Right. So on the outside, this variable, as Anders was saying, is we're hiding it. Right. Mm-hmm. So that means that when we look inside, we discover that this is a request for some A, and we can then pattern match on the request to figure out what that A is. But on the outside, we don't know that. And indeed, like, as Anders said, if we have no structure at all, just some A that we don't know anything about, then this is a completely useless type. Right? It's useful to have some combination of some structure that we know and some things that we don't know.
Mm-hmm. Often you might even still want to know something about the A, but not the exact type, right?
Right. In fact, we're going to see an example of that in a second.
Mm-hmm.
Yeah.
Mm-hmm. Yeah.
So let's first look at a from JSON instance for some request.
Mm-hmm.
So what we're going to do is we're going to decode an object. So now we have an object here that we can get fields from. And then we're going to get the tag. So this is pretty simple ASON style programming, right? This is nothing particularly special. But then if we see that the tag is getTime, then we're going to return not just getTime, but we need to wrap it in this some request in order to hide that result type variable. And if it's getFile, well, then we need to get that file path out of the object first. But once we've done that, again, we need to wrap the result in some request, but now it's getFile of the FP. And any other tag will be invalid. What did I get wrong? Oh, I need to pass it to V somewhere. Here we go. Mm-hmm. All right. Okay, so this looks like a pretty standard from JSON instance. The only difference is that we are wrapping the result in this some request in order to hide this type variable here.
Mm-hmm.
Now, we also need multiple requests. So I'm going to call this some requests, plural. Mm-hmm. Here, we're going to get an NP of request for A's, right? We don't know any of these result types. Mm-hmm. And this is precisely an example of what Anders was talking about earlier. We do actually want some additional information about that A's. And what is that additional information? Well, it's the singleton that we need here. So another thing that you might commonly see is that maybe this thing is showable or things like this. These are common constraints in existentials.
Mm-hmm. Or have some other operation on the A directly embedded in an existential. That is what we have seen last time. Right? Last time, I think I used an ad hoc existential encoded as a continuation at the very end of the episode in order to establish that two structures are compatible. So I was trying to basically hide two different things that have the same type variable. We forget to the outside what that type variable is effectively, but we remember that they're the same. And I think that was
exactly
the situation which we had in the previous episode.
Yeah.
Mm-hmm.
Yeah, so that's a very common thing, right? When you do with existential, this sort of combination of things known and things unknown. Mm-hmm. Okay, so now how do we deal with from JSON for this guy here? Well, let's start with parsing the JSON and getting a list of values out of it. That's just a regular function call here. And now we are going to define a local function, and then I'm going to call aux, that parses all of these values. So if we have the empty list, then the result is the empty N-ary product, and I need to map it in some requests, right, to hide the result type again. And if we have at least one request, then I need to parse it. I get back some request, right? A request for some type. We don't know what that is, so I need to pattern match on that. Then to bring that in scope, basically, like unhide it. then I need to do the same thing on my recursive call. And now in my result, I need to hide it again. So this is also here. So this is also a pretty common thing. Like when you're dealing with parser for this thing that you're opening and then wrapping again. Yeah. Okay. If there are no questions about that, then let's go to the final part, which is encoding and decoding of results. Right? In the beginning, we said that there should be no need to tag the results. Right? We know what the result is. There should be no need for additional information.
Yeah.
So we know what the result is from what? From the request. Right? So we should need the request in order to decode or encode the result. So that makes sense, I think. So if we have an NP of requests here, which we're going to use only to determine how to encode the result, and an N-ary product of all those results, then we're going to turn this into a value. And how do we do this? Well, we're going to do the same thing that we did before. We're turning this into a value, which is a list. So now we need a list of values. As before, we're going to take this N-ary product and collapse it down to something which is really a list. So we're going to collapse NP. Just like we saw above, right? And now we want an NP of values, K of values, right? So that we can collapse it. How do we do that? We're going to zip these two products together. Just like zipping of list, we have zip of N-ary products. And so that means that we're going to pair every request and every response to get the encoding of the result for that request. So
yeah, always the one that have compatible types, right? I mean, just like zip works on lists, but here, because we have the same AS for the NP of requests and the NP of I's, that means that the corresponding positions have the same type argument, like request A and IA here.
Yeah, exactly. Yeah, it can't be that they don't line up. Can't be that they have different lengths, right? They must the types guarantee that these must line up. Okay, so we have a request and the response, and we need to turn this into a value. Now the request is only interesting to tell us what A is. Right? It tells us what the result type is, and therefore we know how to encode it. Right? So we get some response, and I just need to turn this into the result, the value here. Now, this pattern where we pattern match on an I and then wrap in K is very common when you deal with sop-core. So there's actually a function that does precisely this. It's called map IK. So this is just map IK of 2 JSON.
Yeah, but I mean, the sad thing is now, I mean, you can see that you're calling this on a UTC time, right? I mean, if you look at I think even if you now hover on to JSON and look at the inferred type, it doesn't show you the.
I can go back to that.
Yeah.
No.
Oh, why?
HLS not being particularly clever here.
Oh, interesting.
Oh no, here you can see it. UTC time.
Yeah. Yeah. Okay.
Yeah. So by pattern matching on that time, we know that
it looks a little bit weird. Sorry, yeah, it looks a little bit weird. We're calling to JSON twice, but we're calling it on concrete types, right? That we have revealed by matching on the request.
Yeah, exactly. This is the to JSON instance for time. This is the JSON instance for string without any other tagging, right? There's no need to tag anything else.
Yeah.
That's also why I did not need to define new to JSON instances or from JSON instances for the response. We just used the existing ones for those types. And finally, and that's the end of the episode then, decoding works very similar. So we now have a bunch of requests again. And this, again, is just going to guide the deserialization, right? We're not actually needing 2 values. We just need to pattern match on them to reveal the types. And a bunch of values. And we're going to get a parser and an instant parser for these responses here. And I need my singleton again. Okay, so we have a bunch of requests and a bunch of responses. And now in encoding, we went from a list of, from an NP into a list of values, right? Here we have a list, we're starting with a list of values, but we want to zip it with this list of requests, right? So we want to go from a list of values to an NP, which we can do. It's called from list. But this can fail because we have a specific type in mind, right? Ace tells us exactly what the length of this list is. So if the length of this list is not what we expected, this from list will fail. But that's precisely right. We want that to fail because if we don't get the expected number of values from the expected number of requests, we basically have like a
parse fail, not parse file.
Sorry, yes, thank you. If they do match, if the length is correct, then we now have an N-ary product of k of values, right? This is the inverse of collapse, basically. And so now we can just zip them together, just like we did before. And these are now, this will be a list of parsers, an N-ary product of parsers. We want a parser of an N-ary product, and so we need to sequence the result. Just like you would with normal lists.
Yeah, and that works because parsers are applicative.
Right. And now we have a very similar structure, right? Here we have a request which guided serialization, a response turning into a value. Here we have a request guiding deserialization. We have a value in a parser for the response, right? So it's a very nice duality. And again, we don't need to care what's in the request. We just need to care what type the response is. And so we just parse the JSON value after unwrapping that constant functor here. And we do the same thing for get file. And we're done. There are other ways to deal with this. You could, I mean, there's more advanced ways, but yeah, I think this is a relatively simple way to do it. And it very clearly shows that the request does indeed tell us enough information to encode or decode the response.
Yeah, I mean, we
just
can
to show that it
perhaps
works. Sorry, go for it.
Sorry, no, sure. If you want to show that it works, that's more important. Go.
Yeah, I mean, this is, I have, the code for this example is in the repo, as always. I just have a very small mock transport layer here. Did I not call it get all results? Oh, get all requests. Fair enough.
I didn't notice that.
And I guess I missed this decode result as well. same mistake here. All right, good. So I have a very simple mock transport layer that sets up basically a buffer between two things, and then we have the server talking to the client, and the server sends this request, get time, and then get file, and their server responds here with the current time and the contents of this file. And that's it. All right. Sorry, you were saying something.
Very nice. No, I was just saying, like, I mean, historically, like, I mean, the origin of the SOP core library is a little bit that, like, I mean, we developed generics SOP many years ago as a generic programming library, and that was based on these data types. So I think what this episode or what this example really shows is that N-ary products and N-ary sums are just useful types, and that's also why we extracted that into its own package, which is SOP core, and you can use them independently of generics. And there are more functions. I mean, we've only scratched the surface, but there are many nice higher order functions that operate on N-ary products and N-ary sums, and that is also what makes it pleasant to work with them. That you don't have to re-implement everything from scratch, but you have a rather rich library that works with them already. And obviously it's taking some getting used to because everything is a little bit more complicated. And you have to get familiar with the types, but it is the type system also helps you quite a bit. So yeah, I think it's...
Yeah, I mean, even though we developed this, as Anders said, for generic programming, in fact, I think personally, I use SOP core way more than I use generic SOP. So I find this quite useful. I use them quite often. Yeah. No other questions?
No.
All right.
Okay. Yeah. So thank you for watching this episode of the Haskell Unfolder. I hope you liked it. As usual, you can ask a few more questions in the chat if you have them right now. Otherwise, you are very welcome to leave comments below the video. And we hope to be back in a couple of weeks as usual. Thank you very much.